In this video, we will talk about graph data structure. Graph data structure is a set of vertices and edges. We can call it nodes and edges as well. So this is a graph and these are the nodes and the edge which are connecting these nodes is called edges. So graph is nothing but set of nodes and edges. So in this graph, we have these nodes A, B, C, D, E, F. All these are nodes and then we have these set of edges. So A to B is an edge, B to E is an edge, B to D is an edge, A to C is an edge, C to F is an edge, and E to F is an edge. There are two types of graph. One is directed graph and one is undirected graph. So this is a directed graph and this is an undirected graph. The difference is in an undirected graph, if you can see A to B is equals to B to A as well. So A to B is same as B to A. But in a directed graph, A to B is not equals to B to A. Means edge can go from A to B, but it cannot go from B to A because we don't have any directed edge from B to A. Facebook can be an example of undirected graph because I can be friend with someone else and that other person becomes my friend as well. So the direction between me and my friend is unidirectional. Whereas internet, World Wide Web can be a directed graph because one page can have link to another page and it is not important for the other page to have link for the source page. The main operation which we perform in graph is like searching for a node or finding the shortest path from one node to another node. The two main algorithms for graph are BFS and DFS, breadth first search and depth first search. Let's look into breadth first search. In breadth first search, we traverse the graph in level wise and we use queue data structure for performing breadth first search. Queue is a first in first out data structure which we'll be using for BFS. So let's see. So first we insert the first node in the queue and we will mark it as traversed and then we'll put it in the output list. So now that this node, the first node is traversed, we can remove it from queue and add its neighboring nodes, its children nodes into the queue. Now at the top of the queue we have B node, so we will traverse B node. We'll mark it as traversed and put it in our output list and dequeue B node from our queue and enqueue its children node in the queue. Now in the queue on the top we have C, so we will traverse C, put it in our output list, add its children F to the queue and mark it as traversed. And now we can dequeue it from our queue. Next, on the top of our queue we have D, so we will traverse D, put it in our output list, mark it as traversed. And since it does not have any children, any neighbor node which is unvisited, we don't have to enqueue anything, we can simply dequeue this D node. Now the next in our queue is E, so we'll traverse E, put it in our output list, mark it as traversed, and dequeue it. And then last in our queue is E, so we'll put it in our output list, mark it as traversed, and dequeue it. So this is how we traverse the breadth first search. We do it level wise. Instead of going in the depth of each node, we traverse each node neighbors first and then go for the next level, means then go for the children of those nodes. So breadth first search is done in the level wise. And now let's look into the depth first search. For depth first search, we use stack data structure, which is a last in and first out. In depth first search, we go into the depth. So when we traverse A, then we traverse the neighboring node of A, which is B, and instead of traversing C next, we will be traversing its children first. So we will be going in depth in the depth first search. It is not level wise, it is based on the depth of each node. So in this algorithm as well, first we will traverse node A, we'll put it in our stack and put it in our output list as well, and then mark it as traversed. Now the neighboring node of A is B and C. Alphabetically, we will go to B node, put it in our stack, mark it as traversed and put it in our output list. Now the neighboring node of B is D and E. So alphabetically, we'll go to D node, put it in our stack, mark it as traversed. And since this node does not have any neighboring node which is unvisited, we'll pop it from our stack. So we can pop D from our stack and go to the next neighboring node of B, which is E. So we'll traverse E, put it in our stack, mark it as traverse, and then check for its neighboring node. So E has neighboring node F, so we'll traverse F, put in our stack, mark it as traversed, and then go to the neighboring node of F, which is C. So we'll traverse C, put it in our stack, put it in our output list, and mark it as traverse. And now that C is traversed and it does not have any node which is not traversed, we can pop out this C, and F is also traversed. It does not have any node which is untracked, so we can pop F as well. We can pop E, we can pop B and A as well from our stack. So this is how we do depth first search. We go into depth of each node before going into level. So in breadth first search, we traverse level by level, and in depth first search, we traverse in the depth of each node.